Alright, I'm going to show you how to balance one of the more difficult equations in a problem example. When we come across these situations, it's when we're reacting a substance with carbon and hydrogen in it with oxygen. And this always makes water and carbon dioxide. The nice thing is that we always follow the same exact process that we do with all of our other chemical equations. And so you'll know that you have to use this process that I'm going to show you when you hit a brick wall at the end when trying to balance your oxygens out. And so you kind of really have an easy path forward into doing these. It's just you'll hit a brick wall and then, oh, I know I need to use this technique that Mr. G taught us. And it's really just kind of one or two, depending on how you look at it, extra steps. So let's do what we always do. We count out everything we've got. So we've got 12 carbons on our reactant side. We've got 1 carbon, on our products. I wrote 12. We've got 1. We've got 22 hydrogens on our reactant side. We've got 2 hydrogens on our products. We've got 12 plus 2, which is 14 oxygens on our reactants. We've got 2 plus 1, which is 3 oxygens on our products. We need to balance our carbons out first because that's in our most complex compound. So we need to get 12 on the products. The easiest way to do that is to just put a 12 in front of our carbon dioxide. By doing that, we've achieved the 12 we wanted. We've also changed our number of oxygens, so we need to address that. 12 times 2 oxygens gives us 24 plus 1, 25. So we'll change that. Now, let's address the hydrogens. We've got 22 on the left on the reactants. We need 22 on the products. Well, hydrogens are only in the water molecule. So if we have 2 for each water molecule, we need a number to double that by in our coefficient. Well, by putting 11 here, 11 times 2 gives us the 22 we need. We've also changed again our number of oxygens, so we need to address that. 11, and there's only 1, so 11 oxygens there, plus the 24, 35. Okay, so here is where we reevaluate. We've got our carbons balanced. We've got our hydrogens balanced, but we don't have our oxygens balanced. So we need 35 on this side. We don't want to put any coefficients in front of here because why? Well, then we'll have to change everything we've already worked for here because whatever we put here is going to change our hydrogens and oxygens. Our carbons and hydrogens again. So we only want to have to change this number of oxygens to get up to the 35 we need. So we want to figure out exactly how many oxygens matter. In other words, I've got 35 that I need, right? Well, I've got 12 existing here already, right? So I'm going to subtract away the 12 that I've already got from that molecule. 5 minus 2, it's 35, right? Yeah. 5 minus 2, so that's 3. 3 minus 1 is 2. So I need 23 total oxygens right here. Okay? I've got the 12 right here already. So those are going to be what they're going to be. But I need to get 23 existing right here. Right? So if I need 23 right here, I can't just put 12 here, right? 12 times 2 is 24. So that's a little high. I can't just put an 11 there. 11 times 2 is what? 22. So that's a problem. Okay? So here's the solution. I know exactly what I need is 23 divided by 2. That's going to get me the perfect number, right? So why don't I just put that there? Now it's perfectly balanced. I have that exact number that I need, right? That gives me my 35, kind of, sort of, right? But the problem with that is that in reality there's no such thing as a fraction of an atom, which is, this is kind of what this is saying to us, is that I've included a fraction of an atom in here. So we have to fix that, okay? It's kind of like a temporary fix. Well, there's an easy way to fix that, right? We just use our math skills. We say, okay, well, I can fix that by just saying times 2, right? Because if I multiply that fraction times 2, I get rid of that 2. And what I do to one coefficient, I must do to the rest. And that fixes our problem. So I multiply everything by 2. It's like algebra. What we do to one thing, we must do to everything. Okay? So now, I multiply all my coefficients by 2. That gives me 24 carbons on both sides. That gives me 44 hydrogens on both sides. Now I got to reevaluate my oxygens. So I've got 2 times 12, which is 24, right? Plus the 23 times 2, which is 46. So 6 plus 4, 10. 4, 5, 6, 70. Right? 4, 6, yeah, 70. So now I've got 70 oxygens on both sides. Let's see if it holds true for the other side. See if it worked. 11, that was times 2, so that's now 22, right? I should probably just fix this, so that's 24. So 22 oxygens, right? So I've got 22 oxygens there. And then 24 oxygens times 2. 24 times 2, 8, 48, 8, that's 10, 4, 5, 6, 7, 70. Well, hey, look, it looks like everything worked out. So let's write our final balanced equation here. So that is 2 carbon 12, H 22, O 12, plus 23, O2, makes 22, H2O, plus 24, CO2. This was a liquid. Oh, nope, it was a solid. Let's fix that. This was a gas. This was a gas. This was a gas. And that is our balanced equation. And we checked it out to make sure it was accurate. So that's what we do. We hit a brick wall. We figure out exactly how many oxygens that we need on the oxygen molecule itself by subtracting away any oxygens we have anywhere else. And we add that number in front of our oxygens and we divide it by 2. Then because we have to make sure that we get rid of that fraction, we multiply it by 2. And since we multiplied that coefficient by 2, we multiply all the other coefficients by 2, and we'll get our balanced equation.